This is Dr. K. Rajendra Prasad. I am working as professor and head for the departments of data science and also cybersecurity. Today my topic is lexical analyzer generation. So in this we discuss these two ideas regarding to what is the structure of generated analyzer with the interaction of some important components we have to discuss. Another one is pattern matching based on NFA. Nothing but we try to defining some kind of automated simulation, and based upon that how you check the patterns, and also you can determine whether the patterns are valid patterns, nothing but valid lexemes or not. So these are the two major ideas in this discussion. So we have to see that what is the idea of lexis. So previously we have discussed the lexi is a program, that is it given the some kind of services of the lexical analyzer. Means it includes that it gives the idea of the complete lexical analyzer service. So which has the fixed program that simulates an automaton. Because of automatons are playing an important role in the design of compilers or construction of compilers, we should use make use of some finite automatons. So regarding that, how can you implement the finite automaton in the case of simulation? Nothing but with the help of this Lex program. So that is the idea of a fixed program, that simulation automaton. The next one is what are the total different types of automatons you are going to discuss. So we are going to discuss totally for two types of automatons. Means we try to designing a simulation of totally for how many types, nothing but totally for two types. One is deterministic, another one is non-deterministic. So already you had the idea of what is the deterministic and non-deterministic is. From the same source, you are to reaching only for single destination state, or you try to define only for single unique path only for reaching the destination state, that is called as deterministic. Otherwise, it is called as non-deterministic. Means without reading the any input symbol. Means by taking the null transition, you are going to move another state. That is the idea of non-deterministic. One more idea of non-deterministic, nothing but from the same source state, you are reaching to more than one destination states. Means it is possible to define multiple paths from the same source for reaching the various destination states. That is the idea of non-deterministic. So finally, so we have to designing the lexical analyzer for the purpose of simulation of automaton. So that is we have to go for discussing. Along with here, we discuss what are the major components we are getting in the case of designing of lexical analyzer. So that is we have discussed in today class. So this idea of this is a diagrammatic idea of the structure of generated analyzer. So here very important thing is I am going from top to bottom. So this called as the input buffer. Means some space. You may assume some memory. In the memory, you have to allocate some space for storing some lexemes. That's called as the input buffer. So lexemes nothing but that should be identified by the simulated automation. Means the simulated automaton, it can decide whether it is a valid lexeme or invalid lexeme. So how you know that it is a valid or invalid? Because of in the finite automata, so we have to differentiating totally for ending with two different states. What are the states are? Dead state, or is called as final state. So finally, we have to reaching in the automata after reading some various characters in the lexemes, various characters in the pattern. Finally, you have to reaching either dead state or final state. So suppose you are reaching the dead state, what happens? Nothing but So here the lexeme is becomes a invalid lexeme. Means without accepting the all characters of the lexeme, okay, you have to reaching I think unsafe state. It is called as unsafe state. It is called as dead state. Suppose you are reaching the final state nothing but all given characters of the particular token or all given characters of the particular lexeme that is accepted by this finite automata. Means this finite automata simulator nothing but finite automata simulator. It may be for deterministic or non-deterministic, whatever that you are designing, that based upon implementation of the program, Lex program. So sometimes you are interacting with the simulation of the deterministic automata. Sometimes you are interacting with the non-deterministic finite automata. So with help of this finite automata, so finally we have to tracing the characters of the particular lexeme or pattern. It's called as a pattern. So in the pattern, we have to go for the look ahead is characters are one by one. Suppose I am taking the symbols are A B B A B B A. This lexeme start the header is at first character, second character, third character, fourth character. After that, you have to reaching the final state. That's called as the idea is final state. Then the meaning is so this pattern. Okay, what the pattern is A B B A is accepted. Suppose after ABBA, so you have to reaching some dead state. This is some dead state. Nothing but the string is not accepted by the finite automata. Means it is the idea of automated simulator. Automated simulator, it can do the characters matching in the given pattern one by one, according to the transitions in the automata. Means we have to go for like this. We have to go for like this. I give the two symbols A B. He also transitions as A B. So this symbol is matched. This symbol is also matched. Suppose here, unfortunately, here A is there. This symbol becomes unmatched. At that time, interesting is not accepted. This is a way of mechanism you are going to apply in the automaton simulator. With the help of this automaton simulator, so you have to collecting what are the things nothing but valid lexemes. Means you are to saying which are the valid tokens because of lexical analysis nothing but the scanning of the program, parsing of the I think some input data, input pattern. So during the parsing, you're generating some sequence of tokens, a sequence of lexemes. What is the sequence of tokens? Sequence of valid tokens and sequence of valid lexemes. So totally for this validity of the particular token, validity of the particular lexeme that can determined by the automaton simulator. So this is the idea. So how you implement this automated simulator nothing but so by writing the program, by writing the what the program is a Lex program. Lex program is ready. The Lexical compiler it convert the Lexical program that can convert into some actions and also transition tables. Already have discussed what the actions and transition table is. If it's suppose I am taking some control statement, these are the actions. Or some I go for satisfying that control statement, you have to enter into the some particular body of the if block. Okay, the particular statement is executed. Means whatever logic you can define in terms of transition tables and actions. So the Lexical program that can be converted by the compiler into some different actions and transition tables. Already you know that transition table is at what particular source state, what symbol you have to go into so particular output state. This idea is a transition table. So you can implement this transition, I think, function and transition tables, transition mapping values by taking some various control statements like if statement, whatever that the other equivalent if statements. So this is the overall structure of the generated analyzer. So finally, so you can give the idea is of the generated analyzer components. What are the major components you have to discuss in the generated lexical analyzer is three components. One is regard to the function table for the automaton. Means already have to see what the finite automata is. I think set of states and input alphabet, delta, and one more is initial state, set of final state. Here, this component is very important. Delta is some kind of transition function or transition mapping function, or it gives the values of some kind of transition table. Means here you are taking the some states like this. Here we are taking the some input of a bit. This is called as input of a bit. This is called as state queue, and here we have to find the what are the destination states. So using delta of q naught comma a. Suppose for example, I want to go for q1. Here write q1. So this idea is called as the transition table. Transition table. So it means in the automated simulator, when you writing any Lex program, so the important component you have to deciding is the defining the some transition table. How you define the transition table? With what logic you have to describe the transition table in the Lex program. That is the one of the component. One is the functions. Functions that are passed through Lex to the output. It may be for user defined function. Means the transit table that can be implemented cannot directly. So with the help of some associated functions, you should take care of about transition mapping function values. So those user defined functions that should describe in the Lex program. It is another second component. And we have to see the actions from the input program which appears as fragments of the code to be invoked by the automation simulator. So means what are the actions? Suppose I am taking a simple example is here like this, two states Q0 and Q1 here. The meaning is when the transition is A, means you write like this, when transition is A, then the what the output state is? Output state is Q1. Output state is Q1. So this is the action. This becomes some action. So you have to describe what kind of actions you want to define in the functions, so that we can go for define the transition table, the correct transition table. Means these kind of actions, set of actions that you should refer in the input program, which appears as arguments of the code to be invoked by the automation simulator is true, because of the thing is a Lex. Is a Lex compiler. The Lex compiler is have the some actions and giving the idea of a simulator. Okay, automation simulator. What it will do? It will decide the whatever the patterns are stored in the input buffer. It will decide whether the pattern is a lexeme, valid lexeme or invalid lexeme in such a way that it produces the output is some sequence of lexemes. So this is the particular outcome of a generated analyzer. So what the outcome of generated analyzer? But producing some lexemes by the automated simulator, which is being implemented by some in the using the Lex program. Okay, this is the major idea of the generated analyzer. So we have discussed the thing in terms of some practical orientation. Yes, it's true. Is initially we have tried for constructing the some automata. It is required. So maybe for what purpose nothing, but I think we want to initially we have the input is regular expression only. The regular expression need to convert into equivalent to NFA. For that point, you need to construct the automata. Means you have many regular expression. You want to describe what the corresponding automata is, the corresponding NFA or DFA of the regular expression. At that time, you need the knowledge is how can you construct the automata. This is very important when you I think implement the various components of generator analyzer, and after that, after design this NFA, okay, it recognize. Okay, that's point we have discussed. This recognize the lexemes. All I have discussed now. Suppose it's I think some idea of some pattern, whether it is valid or invalid lexeme. How can decide that? We go for character by character. Okay, all characters are matched, and at the end you have to reach the final state. Then it is a valid lexeme. That lexeme is accepted by the corresponding designed NFA. So the same thing is discussed in this point. An automata recognize lexemes matching any one of the patterns in the program. Means many patterns are there because of language nothing but you cannot depend only single patterns. Language nothing but they have the many number of patterns. So for each and every pattern, you are assuming some regular expression. So every pattern case means every regular expression case need to construct some separate NFA diagram. So for the NFA diagrams constructions case, so you have to referring mainly is for our language patterns because the main theme is any given programming language or any other than programming language also. So how you can decide the language, the given patterns are language patterns or not. So those patterns that can be uh, simulated by the finite automata and reaching to final state after accepting the each and every character accept method, but after matching the each and every character, finally you have to reaching the final state. Then that pattern is called as lexema pattern, value lexema pattern. So this majorly we have to focusing in the generated analyzer. So we have discussing this point is in a simpler way is an automaton recognize the lexemes means patterns matching one by one of the characters, one by one the characters of the given patterns in the program. So one more thing is here not only for the single patterns in the language, massive number of patterns in the language means so those massive number of patterns mean we have defined some collective some equivalent regular expressions. So massive patterns, many massive patterns requires at least some of the regular expressions. Therefore, some set of regular expressions, you should cover massive number of patterns. You should cover the massive number of patterns. For every pattern, need not describe the unique regular expression. Some of the pattern case we describing only for single regular expression, that is enough. So here the expressions are in the way is similar way. Okay, here we describing only for single regular expression. The patterns are not described in a single similar way. It may be in dissimilar format. So we have defined some different regular expressions. So that is based upon that we can find out how many number of regular expressions are required for describing the all language patterns. For describing the all language patterns. Once you know the clarity about the regular expressions for describing the some language patterns, so then it is very easy to construct the finite automata. So therefore, the simulating the particular finite automata, you try to generate only for the valid lexims only. That is given in the last point. Means many regular expressions are possible for describing the some all patterns of the particular language. For each and every regular expression, you must define the separate finite automata. By combining all different finite automatas, you have to getting the some idea is you should accept each and every language pattern, but beyond the language patterns, okay, you cannot apply, you need not apply the particular finite automata. That is given in the last point is combine all the NFAs into one by one by introducing a new start state with the epsilon transitions to each of the start states of the NFA. Nothing but this is one NFA, this is another NFA, this is the third NFA. So how can you combine nothing but with the epsilon symbol? With the epsilon symbol, we should combine different NFAs. So this idea of start with the epsilon transitions to each of the start states of the NFA because of so you're designing NFA for each regular expression. That's the first point, and you are getting many NFAs. How can you combine those many NFAs, or how can you mix those any NFAs nothing but with this different epsilon transitions? You should combining. I should image many NFAs. So that is we have discussed. These 3 points are very important points. So you should describe the what is the diagram for the this generated analyzer, generated lexical analyzer. What are the important components? What will do? Okay. So I think construction of the automata and lexemes, how you identify the lexemes, and what is the need for combining many NFAs. Okay, so that is the basic idea about generated analyzer. So we have to discuss along with this, and example illustration is very important because of here I am showing clearly 24 how many regular expressions are? 3 regular expressions. Okay, this is the one, the second one, and the third one. So this regular expression, what the corresponding automata is for accepting this pattern. Okay, what the pattern is here? P1 is equal to A. So what is the second pattern? P2 is? P2 equal to is also constant pattern ABB. What is P3 is? P3 describes this is some different way A star B. Nothing but you can write what the A star is. A star nothing but null symbol, single A, 2 A's, 3 A's, and so on. This is called as A star with B. Another one is B. So finally, you can write A star with B nothing but B with null value. You are getting the B. B with A value is BA. B with A is BAA. Right. Means what is the pattern you are assuming? Sorry, it is a B plus no. Okay, it is a B. Okay, B plus nothing but you know the idea. So excluding null value, you can generating single B, 2 B's like that. Okay, you are assuming it is B. You assume for B case I am defining the solutions like this. This is a pattern P3. So here we have totally for how many number of patterns? 3 patterns. Means the meaning is 3 regular expressions are required. 3 regular expressions are required. For every regular expression, you describe the separate NFA. So this I think NFA for which pattern is P1 pattern. This NFA for P2 pattern. This NFA for P3 also. Okay. Here I given. So totally you can imagine how can you imagine it with epsilon transitions. So already got totally for 3 NFAs, NFA1, NFA2, NFA3. You can imagine like this. Okay, it is a I think idea. So basically pattern matching after combining all NFAs you get back on complete automated diagram. Once the automated simulator is completed, then what the process is? So you should provide some input. No, you find the tracing of the characters of the input. It moves. The pointer moves ahead. The input for matching patterns of the other symbols of the input. Okay, and like that we have to move one by one the characters. Suppose I am taking the same pattern already discussed. We discussed in the last PPT, the last slide, and it is a one. It is okay. It's matching is okay. Then you go for this pointer is next to move to next forward, move to next position. It is also okay. Okay, like that. Finally, okay, yeah, all characters are accepted. Then it is called as a valid exit. Valid exit. There's a discussion for pattern matching based NFS. So finally, we have to see the examples. These are, I think, the pattern, the regular expression or pattern equal to A. So this called as what the pattern this automatic is implemented. The another pattern is P2. Okay, you have to check A, B, B. Okay, it equal to A, B, B, B. So another third regular expression is regular expression, or I'm taking the pattern now. Regular expression is P3 equal to A star and with B and B star. B with B star. What happens? A star with B plus. Okay. So the regular expressions of A, the regular expression of ABB, the regular expression of A star B plus. Okay, you have to design separately these 3 cases, and finally you can merging all these 3 in this way. You can match. This is a P1 pattern. This is a P2 pattern. This for P3 pattern. You can match using the null transitions. This is a way for constructing the NFA for on a particular language. I am assuming language nothing but the symbols are A, B, B, and A star B. In this language, so these are total for 3 patterns. So 3 NFAs are required. These 3 NFAs are merged by using this syntax, by using the null transitions. This is the way for NFA1, NFA2, NFA3. These 3 are merged with the help of this null transition symbols from the starting state. This is the final NFA for or particular language. Okay, what the language is? Language is A, ABB, A star, B. So finally, when you again the idea is a pattern matching. No, this is one example scenario for pattern matching. This I think in what way the patterns are matched. Here I am showing very clearly. So the pattern matching is here I given A, B, A. Okay. So for A case, so first character case, how many possibilities are there? I am showing the possibilities are here A is this is A, this is A. Okay, where it is also A. Nothing but 0, 1, 3, 7. The same thing is described 0, 1, 0, 1, 3, 7. After A, after accepting the A, again the second one is well also A. Second also A. So you have to check the previous one is after this A, the second is also A. Nothing but where is that possibilities? You have to check it very clearly. So we have to getting the 2, 2 and also 4. 2 and also 4. Yes, 2, 4 and also say that 7 is also 7. Yes, it is also 2. This is a self group now. 2, 4, 7. So like that you have to check it whether this string is accepted by the particular automata or whether it is a language string or not. I want to determine the thing is A, B, B, A. Okay. The question is language string or not? String or not? This is the question. Regarding that, I'm going to implement the finite automata initially. The second step is pattern matching based upon the availability of the transitions and states. Finally, then describing. Okay, finally, however, this string is enter string is accepted. This is a tracing of this is a pattern matching process of a given the string is A B A B A. So finally, A B is accepted by the NFA. So we are concluding that this is for the language lexeme of language pattern. So this is the idea. Like here up to now I have discussed the NFA simulation only. Like you try to simulating once NFA is I think in your hand, so then you are going to NFA to DFA conversion. Already we have discussed that conversion also. So after converting the NFA into DFA, you are getting the states like this. Okay, so this is not 0137. You can rename as this entire 0137 as some state name. Okay, S1 you call is the S2. Okay, and this S3. Because of why you are getting the 0137, but after applying the conversion of NFA to DFA, some states are merged. Okay, the states are merged or 0137 are merged. So now you can read as 0137 state name, or you can give some rename. Rename of the state is S1 equal to 0137. Okay, so now you can call as S1, or you can suppose you don't have any confusion, you can read as 0137 state only. So means this DFA you obtained from the corresponding NFA diagram. So I think this I think finally you got the DFA. Again you write them some next program, and means what are the declarations. First part is what are the actions, like if statements or anything. What are the functions, auxiliary functions. So try to take these three components of the lex. Okay, declaration, actions, and auxiliary functions. With the help of this structure, lex structure, you should write the program in such a way that you try to simulating the some DFA diagram. So after simulating that, so you can verify that whether the language patterns are properly accepted by this DFA or not. By this DFA, all the language patterns are properly accepted. Now it is I think you consider as the correct DFA for given a language. So means this total today class, the idea is basically, so what is the structure of generated lexical analyzer? What are the components? With the help of the lex program components, so how can you simulate the finite automata? So after simulating the finite automata, how can you describe the pattern matching? These are the important discussions, and this covered in today along with the example illustrations. So and I have referred the entire idea from the textbook of compilers principles, techniques, and tools, which is based on education, and the Aho Ullman, the other authors are also there, Ravi Sethi and Jeffrey. So this is the important reference for about today class. So with this, I am concluding the class of generated structure of particular lexical analyzer for the purpose of determine the lexemes, which is done by the simulated automata. The simulated automata it is happened after implementing the program of Lex program. So this is about today class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.